Okay, hello. Thank you for coming and for getting here before me as well. NoSQL has been mentioned a couple of times at this conference already. I'm going to mention it a couple more times. So who am I? I'm Matthew Revell. I work for a company called Couchbase. We make database software of the NoSQL variety, and I will talk a little bit about that. But first, I want to introduce you to something that I bought recently. This is my toaster, and this is actually the model I have. I have the black one, but the red kind of went better with my color scheme, so I took that photo. I mean, I literally took that photo off the internet, so I hope that's okay. Bosh. The reason I'm talking to you about my toaster is because it's actually quite interesting for this talk, because it has redundancy built in. You can see it's got two slots, so if one of them breaks, I can carry on toasting at least one slice of bread. It's balanced for both input and output. It's not optimized for either. I can put toast in and just as much, bread in and just as much toast comes out. So that's great. I don't want to say anything bad against Bosch, but it is actually commodity hardware. So, you know, these are fairly standard off-the-shelf components, I expect, assembled into a lovely shell, but nothing special there. And if I want to make a lot of toast, it's easily clustered. I can set up several of them. One of them can fail and it won't take down the entire cluster. That's fine. I suppose perhaps if they're all plugged into the same outlet, that might cause a problem. But, you know, generally speaking, they work fairly well. And perhaps my favorite thing, because it makes it really, really cool and of the moment, is that this toaster is 100% NoSQL. There is no way that I can access any of its functions through the structured query language. And I think you'll agree that's important, because NoSQL is really cool. Moving on, a brief history of data storage. This is data. This is a clay tablet from Mesopotamia, which is kind of like northern Iraq right now. And this is one of the earliest pieces of human writing that we have evidence of. And very much like how mathematics developed in Egypt to allow for taxation, you know, the best guesses that archaeologists have about this kind of writing is that it's to do with taxation. So it's very much like the sort of data that we're storing now, right? It's to do with business things. And you know, I was actually quite curious to get more information on what this is. So I fed it into Google Translate, and it's true. It's all about agricultural stuff. So, you know, that's what people have been doing with data for a very long time now. You know, this is data as well. This is a Jacquard loom, the first instance of a machine that could take a set of instructions and then do exactly the same thing that another similarly spec'd machine would do with those instructions. I mean, this is about making silk weaves and things like that, but that's fine. It's only in 1960 that we get to the world's first commercial database, the IBM and American Airlines Sabre system. And this is a thing that really, you know, it's almost generous to call it a database. It's basically a file system that took airline bookings from 90 minutes, where you're going through cards, to about 5 minutes, where you're waiting for a very slow computer to check availability. But nonetheless, it's a real database. And I have to say this, but Sabre are now a Couchbase user. Okay, so the whole point of this is to say that we've been doing things with data for a very, very long time as human beings. And it's only in the past 50 years that we've been doing things that we would call databases. And it's only in the past 20 years or so, 25 maybe, that we've been doing relational stuff. You know, it was 1970 that E.F. Codd released the paper describing the relational model for data. It was a year later that two of his IBM colleagues put out another paper that described the structured query language. One of those people now works for Couchbase. So anyway, so the point is that the relational model is great, but it's not the only way of storing data, obviously. And SQL is great, but we've kind of had all sorts of different ways of storing and querying data. And the big thing to say is that actually the data model, the way that you're storing your data, the way that you shape your data very often determines the way you query it. Okay, it's a two-way street. The way you query it determines sometimes how you store it as well. So I want to quickly look, as promised in the abstract for this talk, at different ways of storing data and querying it. So that IBM Sabre database, the hierarchical database, often called the go-to statement of databases, because what happens is you basically work your way through the different links until you find the thing you're looking for. So a hierarchical database, if you are a Windows user, you have probably fiddled with the registry at some point. It is a hierarchical database. IBM's IMS is the evolutionary successor to the IBM Sabre system. It's a hierarchical database which is used in big finance institutions and places like that. And one that you might be more familiar with is XML, or the DOM. You know, this is, if you think of the DOM, then that gives you an idea of what a hierarchical database looks like. So as a developer, when you're querying a hierarchical database, you're basically always going in at the top and working your way down. And okay, that works for some situations, but for actually relatively few is it actually, efficient. So if I want to find, I'm not sure why I chose this particular job role here, but if I want to find the head of event marketing, then I have to go in at the CEO. No, that's not the head of event marketing. I then follow various routes down until I find the person I'm looking for, or the record I'm looking for, and then the associated data with that. Quite limited in its applicability, certainly quite limited in its queryability, because you are telling the database what to do each time you fail to get the thing you want. You're not saying, this is the thing I want. So beyond that, mid-60s, the hierarchical database made way for the network database. So instead of always going up and down, you could have peer-to-peer relationships between data. And you can kind of think of it as a big linked list. And it actually came out of the Codicil working group, who created COBOL and came up with various other things. You can see Grace Hopper there. I don't actually know any of the other people there, but they're all important as well. And it looked like this. So you'd have a record, and then you want to find all the peers of that person, perhaps in an employee database. Then you can follow links, like I say, like a linked list. Again, you're navigating around the data. You as a developer, you're saying, do this. If it's the right data, stop. If it's not, then do this. And so you end up writing COBOL, and that's fun and everything. But yeah. So 1970 comes. We have the relational database. So we go from hierarchical to network to relational with structured query language. And there's a guy called Francis Fukuyama in about 1989, 1990, wrote a book called The End of History and the Last Man. And he declared that all the ideological wars in the world were over now, and we basically had settled on the Western system, and there would be no more great wars. And well, look how that turned out. Because obviously, we haven't stopped having wars, and equally, life hasn't stopped with the advent of relational. So with relational and SQL, we had a declarative data query language, finally. It was a way of telling the database what we wanted rather than how to get it. So that was good. And then, object-oriented programming becomes a thing. And everyone says, well, we're flattening our data into tables when we've got these beautiful objects. And the world said, nah, don't really care. So object-oriented databases, or object databases, kind of were a thing for a few years, but I don't know. Again, you see them in very limited applications, things like Vertex and, I don't know, those kind of things. And then 2005, there was what you could call a Cambrian explosion of open source NoSQL databases. A lot of them answering questions that nobody had ever asked. But yeah, I'd say it kind of kicks off with arguably CouchDB, which was an answer to the question, what would an open source Lotus Notes look like? And genuinely. And so we have CouchDB, and then a few years later, not many years later, Amazon come out with the Dynamo paper and describe this big distributed key value store. Google from Bigtable, someone mashes them together and creates Cassandra. And anyway, so let's have a look at some ways of querying these various NoSQL databases then. So you have key value stores, where you give the database a key and it gives you back a value. And the database doesn't give a damn what the value is. So it could be text, could be JSON, could be a binary. It doesn't really matter. The data is kind of opaque to the database. And that's fine, that gets you so far if you're caching things or whatever, but the query method, again, is kind of limited. So, you have then document databases where the database kind of functions like a key value store in some ways, but then gives you additional insight into what's in the thing you're storing. So, if we're storing JSON, then, we have some understanding of what's in that document. So in this case, I could create indexes against two things, and then I could go and run a query which would give me all the people from who match those criteria that are in those indexes, and I could munch them together, and I get all the people from Couchbase London who work in the developer advocacy team, and that's great. But again, the way to query that is perhaps to write MapReduce queries. And I don't know if you've seen the cartoon where there's someone saying, so Bob, you're telling me that to query this I need to write a MapReduce query in Erlang? And the guy said, yes, I did just tell you to go, don't take this camera, to go fuck yourself. So query has been a long and hard problem in non-relational databases. Because a lot of the time, the idea was, it's not our problem. We're just storing data. What you do with it is up to you. Then there's, I'm kind of skipping over these, there's column stores like Cassandra or HBase, which are really great for time series data and doing massive range queries over them, and then get munged into all sorts of other use cases as well. But we'll look at those again in a little bit more detail. Then there's graph databases. I'm pretty sure I flew very close to Kaliningrad on the way here. And so this is the 7 bridges of Königsberg problem. And if you don't know the story, the Kaiser was visiting what was Königsberg, is now Kaliningrad in Prussia, as it was then. And Euler was a local mathematician who wanted to work out, is it possible for the Kaiser to visit all of Kaliningrad without crossing each of the bridges more than once? And he developed an entire branch of mathematics to say no. And that was great. So graph databases are really good at, they're really good at finding out whether certain Doctor Who characters were in different episodes, if you've ever seen a Neo4j presentation. But they are really, really great. They do interesting things like allow you to have an automated parcel distribution service that in under a second works out which is the most efficient route to punt a parcel off based on its address, and things like that. And they do lots of interesting criminal fraud checking and things like that. So query is really, really important to graph databases. I often think of graph databases as an elaborate query method on top of some other data store, because often that's how they operate. The important thing, though, is that context is all. So we've gone from this idea of storing everything in relational databases, firing up MySQL or Postgres and then writing some PHP. I don't know, whatever it was that we did in the early 2000s. And then there's this idea of polyglot persistence. If you know Martin Fowler, he's a ThoughtWorks consultant who's written a lot about NoSQL, and he introduces this idea, which isn't rocket science, but it's good to give it a name, which is that you use the right database for the problem that you're solving at that time. And that might mean that in a very large production system, you're actually running 4 different database engines to solve different things. So basically, it's about making the right trade-offs. So if you're doing a very simple kind of caching thing, then maybe Redis or Memcache or Couchbase would be the right thing for you. If you're doing mainframe offload, again, it might just be something where you're doing asynchronous processing in one system and then putting it into another system to be punted out to the end user. If you're optimizing for queryability and matching relations across multiple bits of data, then maybe it's a graph database. So the point is to be careful in choosing your data store, because the data model it gives you determines how you're going to query it a lot of the time. And the way that you query it is really the value that it offers you. So what have we done in terms of querying NoSQL? Those past 10 years of that open source NoSQL, I'm not going to call it revolution because that's too grand, but movements, let's say. Well, I hinted at this earlier. The first approach was to say it's your problem. I couldn't find a picture of an ostrich burying its head in the sand because that doesn't happen apparently. But yeah, there's an ostrich anyway. So the whole thing was, well, what we're going to do is we're going to solve these problems like scalability or redundancy or whatever. All that stuff about querying that you've been wanting, well, that's your problem. You do that in the application layer. So that made non-relational databases or some non-relational databases appropriate for only a number of use cases, and a small number at that. And, you can get around it. You can do manual secondary indexes, so you could create your own indexes on the data by, having a document that looks a bit like this. So, you basically have a document that you call people, and then you have the key names of all the documents that store their user profiles. Okay, that works, and it works in practice, and it lets you go with the grain of the database. You're not trying to do things that it's not comfortable with. But yeah, it works, but it's also more work for you as the application developer. And then things like CouchDB offered MapReduce. So we're talking about generating secondary indexes manually by writing MapReduce queries, this time in JavaScript on the screen, but like I said earlier, in Erlang for CouchDB and some other databases. And what we're talking about here is non-declarative query for NoSQL. And yeah, if you're making trade-offs that aren't necessarily query important, you're deciding to trade off query for some other thing, then maybe that's okay. But actually, when we're building applications, we need everything. We want the lot. We don't want to say, well, I tell you what, I want really good query, but when I do a schema update, I'm going to have an animated GIF of someone digging the road on my website because it's not 1997 anymore. So declarative query in the NoSQL world. What do we have? Well, there's kind of three strands. There's database management system specific stuff that you will have to learn a whole new thing just to query that database. Then there are really bold new options, which are kind of flags in the ground of people saying, this is what we should be doing as an industry. And then there are just SQL derivatives, which is where the title of this talk comes from. NoSQL is a lie, because all the NoSQL databases are kind of putting SQL back in somehow. So MongoDB is a good example of the first one. You have, it's a document database, so it gives you insight into the content of the documents, and it makes you learn its own query language to do any of the query. So it's not hard. This is what you would do in the Mongo REPL environment. You're specifying the database, then the collection within it, and then what you want to do there and what you want to find. And okay, it's not hard to do, but it means learning something new, and it doesn't come with 40 years of tooling and understanding that you might have with something like SQL. So bold new options. XQuery. XQuery is for the XML world, and JaySonic is XQuery for JSON. So if you can imagine, basically you're on an advisory board who have created a query language for XML, and you see JSON taking some of your thunder. You want to make your query language happen for JSON. So JaySonic is a declarative query language for JSON. Unlike SQL, it's set-based. It's not tuple-based, and it looks a bit like this. So you want to do a query where you're finding everyone from, again, employee profiles where they've served more than 2 years. So it's much more like, it's much less like writing SQL and much more like writing, just, I guess, pseudocode in a way. But yeah, it's much more like writing a modern application development language than something that was created in the 70s. And it works. It lets you do fairly interesting things. You can change the data in place in the query and so on. So it allows you to return data in a form other than which it was stored in the database. Because a lot of the time with these NoSQL databases, it will just give you back what you stored. So JaySonic's a nice idea. You can do joins across documents. So, it kind of, I'm not entirely sure about introducing try catches into a database query language, but that's what they went with. And, it's an interesting academic exercise. I think one of the problems is that no NoSQL database or any other database has actually implemented it. One of the reasons perhaps is that it's unfamiliar. Another reason is probably political. But you can get plugins for database or connectors for databases which will pipe your data into the JaySonic world and allow you to query it that way. But yeah, you won't be able to get an off-the-shelf database, open source or otherwise, that does this natively. So, like I say, it's kind of a nice idea, but yeah. So why SQL? Why SQL for NoSQL? Well, in this hastily chosen Creative Commons image, I'm trying to show tooling. There's a lot of tooling, there's a lot of knowledge, there's a lot of experience around SQL. And okay, SQL and the relational model seem to be very, very tied together, but I mean, if you actually read some of the academic work around relational databases in SQL, you'll see that SQL isn't actually an exact fit for the relational model. And the really SQL just happens to have the weight of history with it. All of us can write a SQL query, all of us are familiar with it, and there's a ton of tooling around it, a ton of education. So people have been implementing SQL in NoSQL. Probably the first would be Cassandra with Cassandra query language. It really looks like SQL. Schema's a thing again because of the underlying data model. There's no joins, no group by, again because of the underlying data model. And it's not an ad hoc query language. You really have to think about how you structure the data in order to achieve the queries that you want. So what do I mean by that? Well, if we want to store data about authors and then query it, we might create a table in this way. So far, it looks very much like relational-based SQL. But the first thing to note is that the primary key, the first part is determines how the data is distributed around the database, because Cassandra works as a cluster and has a Dynamo-like hashing algorithm and to shard data around the place. And then for our querying, the important part is the next two parts of the primary key. So the year and the title here determine how that data is ordered on disk. So you need to, when you're setting up your data, you need to be very aware of how you're later going to query it. Because particularly if you have large amounts of data, then the way that you order it needs to be optimized for how you're going to query it. So what do I mean by that? So let's put some Tom Clancy books in. Looks like SQL again. And that's the CQL view of the data. And then actually stored on disk, it looks more like this. So you can see that, I mean, there's only like a couple there, but it's ordering things by the year of publication. And that's important because we're going to do a range query. So we want to find all of the Tom Clancy books where they were published before or, sorry, after or in 1993. Well, because we're storing it by order of publication, we can do a very, very efficient range query now. So that CQL query is translated into basically going bom, 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 stop. Because the first time it hits a book published in 1991, it knows by the ordering on disk that it won't find anything relevant afterwards. Now, if you want to do some other query that isn't supported or optimized in the way that the data is stored on disk, it will be much less efficient. So this is what I mean by it's not an ad hoc query language. It's a language for giving you that sense of comfort from your SQL background, but still where you have to very, very much understand how Cassandra works as a database. You have to understand how it's storing stuff on disk. I'd bet that most people here are web or mobile developers and probably not storing, I'm guessing, data every 5 minutes from some remote oil pipeline that's telling you the flow rate, which is what Cassandra's really great at. Instead, you're really interested in JSON. I apologize for this slide. So we want a SQL for JSON, right? We want to be able to query in a way the data that we're storing in our familiar, friendly JSON format in a language that we know. So there's this thing called SQL++, which came out of University of California, Berkeley. And they started off with this idea that, SQL is well known, so we should try and apply it to JSON. And they said, well, what do we do with SQL to make it work with JSON? Well, we need to make it work with semi-structured data. So the first thing to say is that JSON data, NoSQL databases, non-relational databases are not about unstructured schema-free data, because all data has some kind of schema. It might be a one-off for that particular record, but there is a schema there, unless you just, I don't know, sticking a microphone out the window and measuring the decibels in the street or something like that, I don't know. But generally speaking, you're storing something that has some kind of structure. So we call it semi-structured. It's going to be heterogeneous, it won't all be following the same format. And you want to put JSON in, so you want to get JSON out. And so those were kind of the founding principles of SQL++. And so to make SQL friendly to JSON, you need to first break the first normal form, which says that data must be at its most atomic, most basic level. You can't nest data. Sometimes data is missing. That's fine. It shouldn't freak the query engine out. You will break the third normal form, so data will be repeated around the database. And joins need some special attention because you're working with a data model that wasn't created just to enable joins to happen. And there's an interesting paper on the internet about it. If you Google SQL++ paper, it's a lot easier than me providing you with the URL to the academic paper itself. So they created this superset of SQL, which does all those things. It handles nested data, it handles missing data, and it's JSON native. Okay, so Nickel is a language which implements pretty much most of SQL++. Nickel is the non-first form query language, and that's something that came out of Couchbase. But it's open source, and it's an open specification, and we welcome other people to implement it as well. So very, very quickly, this isn't a product pitch, but to put it in context, Couchbase Server is basically a distributed database that has built-in memcache, so it's a distributed memcache. It's a key value store, document database as well, because it lets you do querying of the documents inside, and it has this Nickel SQL-like language for JSON. So Nickel implements a lot of SQL++. So you can write SQL queries that are ANSI 92 compliant and just look like SQL, but then you can do other things like diving into nested arrays and objects. You can deal gracefully with missing data and so on. So let's have a look at me in this kind of database, or in a JSON document. So you can see that we've got an array, we've got some objects with arrays. In some cases, some data's missing, some data's there. So we can do things like we can find all the people in that database who happen to have an office of London. And the interesting thing to say, well, semi-interesting, is that in Nickel, because the namespacing is much wider than a table, you have these collections of data, or as we call them, buckets. The select from isn't redundant, but it does a lot less work than it would in a relational database. So you have to do much more work well, not much more work, but you have to treat namespacing in a different way. And effectively, that's by putting a type in the document or something like that. So we'd run that, and it gives us basically a load of JSON back. And it gives you some metadata to say how long it took. Don't be scared by that. That looks very long, but I hadn't set up indexes on here, so it was the equivalent of doing a full document scan, and I did it on my laptop. So don't take those numbers as benchmarks. But it's JSON, so we have arrays in there. So I want to find a certain conference within the conference array. So this is the first time that we kind of veer away from SQL, but it's nothing surprising. We specify the level and then the key that we expect to find at that level of the array. And we end up with a list of conferences that people from my team are going to. But there's some repetition there, and there's some blanks because some of the documents that it went over don't have that conferences array in them. So we want to deal with that. So we want to throw out the the repetition, so select distinct, nothing special there. But then we can say where conferences is not missing. So this is where we're dealing with the fact that JSON is naturally going to be semi-structured. So we go in, and we can get a nice clean list of all the conferences that my team was going to at the time that I wrote this. And then if you want to find the actual conference that a particular who's going to a particular conference, we can then look inside an array and say, well, inside that array, we want to look for conferences where the event name is DroidCon Sweden. And that would give us back the people who are going to that event. So my colleagues Martin and James went to DroidCon Sweden, and yeah, there we go. So, it's a CRUD database, so you can do updating and deleting as well, and this is specified in the SQL++ paper. You can do what you would expect to be able to do just in the fairly standard SQL way. How much time have I got left?
10 minutes.
Okay, so I want to show you a larger data set to show something more interesting. So with Couchbase, we provide this travel data set. And it's basically a load of airports, a load of airlines, some routes between airports, and then kind of that gives you some flights and some useful things you can do. And this gives us a good opportunity to show joins in a non-relational database. So what do we want from a join? Well, we want to retrieve data from multiple documents in a single query. We want the data that comes back to be the data we want to use in our database. We want in our application, we want the database to do the hard work for us. And so we can do not joins across tables, but in this case is between documents. So in a relational database, an airline might look a bit like that. The airport might look a bit like that. And we might have flights where, again, as another table. In JSON, it would be a very similar story. We have an airline, we have an airport, and we've decided to embed or nest the geodata there, but that could have been top level, I guess. And then we have routes. And so here, instead of having individual records of flights, we have a single route document for that airline between those airports, and then the times and days at which it flies and what the flight number is. So LHR to SFO is a fairly common United Airlines route, and you'll have, I've truncated it there, but you'll have all the times that it leaves on each day. So you want to do a join. So what we're doing here is, let's start at the bottom. We are looking for every document where the source airport is LHR and the destination airport is SFO. And then we're going to take out of that, there's going to be a record that we know there'll be a record called airline ID, and we'll do a join. We'll take that airline ID, and we'll find a record whose key name matches airline ID, and then join it back into a single query. So that's okay. Kind of less useful, I guess, but it'll give us all of the airlines that come back with that. And this is where I fire up Couchbase and hope that this works. So, okay, my apologies, I'm not sure which way. There we go. So if I now try and remind myself of exactly where I've left my CBQ tool. So we've got a REPL in Couchbase called CBQ, which lets you do what you would expect, run your queries. And yeah, this is where I end up probably wasting time slightly. My apologies. I tell you what, for now, take my word for it. It will give you back a list of the airlines. And then you go through and you want to do something a bit more interesting, so you want to split out the actual names of the airlines that are running that that route. So yep, you can do that. But really, okay, so you've done a join, but what you're getting back is data that is still very much in the format that it exists in the database, just munched together. So we can use something called a nest, which allows you to dive into nested data, pull it out, and make it a top-level part of the query. So it's almost like doing a three-sided join. You're joining two documents, and then you're using data nested in one of the documents to then further, narrow down your query. So we can do something rather long like this, which is very similar to what we just did, but you're still looking for source airport of LHR, destination airport of SFO, but then we're aliasing the schedule array inside the routes document as S. We're pulling it out and we're calling it S, and then we're able to use the day and the time from S to say, well, only actually give me the flights that occur on a Monday and order them by time. Then that gives us a nice result now of just the airline name, the flight number, the time it leaves at, and where it's going and what sort of plane you're going to be going on, whether it's a Boeing 777 or whatever. And that's about it, really, Nicole. So like I say, it's pretty much SQL++ as defined by the paper. If you're familiar with SQL, then it's not hard to get started with. I think in general, non-relational databases are very clearly here to stay. I mean, that's goes without saying. But I think that it's less reasonable now for database vendors or open source projects to say, well, we're solving this one thing that you had problems with before, like uptime or whatever. So you now have this whole other set of problems, whether it's query or whatever. I think increasingly, we need everything. We need query, we need the uptime, we need the redundancy, we need whatever else speed that they're offering, but all together. So I think it's going to be an interesting time for non-relational databases in terms of people coming up with interesting ways of querying them. What I would say is if you're choosing a non-relational database, then be just as careful at looking at how you query it and how the data is stored as all the other shiny things that they offer you. If you're interested in Nickel, then we have a developer portal. The SQL++ paper is best Googled rather than following the link. And if you want to ask actual questions about it, then we have forums at forums.couchbase.com. And I think I've stopped with a few minutes to spare. So yeah, 4 minutes. So if you've got any questions, then great. If not, I'll be around.
In the last example,
yeah.
joining from the same table as the first select, was it the type or?
Yeah.
Travel sample and from travel sample and then join travel sample. Is it type or?
It's travel sample is the bucket. So a bucket is.
Okay.
Yeah.
Yeah, I get it.
It's a very high level namespace where you can have millions of documents, essentially. So you're doing like an inner join inside it's almost like just specifying the database rather than the table. So in Nickel in particular, in SQL++ as well, there's this concept of key spaces. And key spaces should be a level of namespacing below the bucket level.
So, but in the same namespace, you can have documents with completely different channels.
Yeah, totally, yeah.
So you don't put different documents with different channels in a different namespace?
Well, I mean, you would if it was purely a namespace. I mean, in the Couchbase case in particular, a bucket is just as much an allocation of resources as a namespace. So when you have the indexes running across Couchbase, they run across a particular bucket. So yeah, buckets have a different role than just a pure namespace. So with this example, I know in this dataset there's 34,000 documents. So running over that as the equivalent of a full table scan would take a little while. So we've built an indexing engine that sits under it, which allows you to create secondary indexes as you would in a relational database, and then change the query time by orders of magnitude. But yeah.
Yeah, time is off.
Okay, thank you very much. Oh,
What about execution plans? Like, if there are some indexes beneath it, how does it choose which indexes are better suited, which ones to scan first?
yeah. So I mean, I'll be upfront and say I don't know. I think it's best just to say that. So this is like our first release of Nickel. It's a long-term project for Couchbase. There are people using it in production. For example, DirecTV, their EPG runs off it, interestingly enough. So it is being used in production, but what I would say is it's kind of a long-term project for us to bring queryability to a large-scale document database. So things like, I mean, the language itself has been around for about 4 years, but it's been working on things like execution plans, making sure that it's as performant as possible, that have stopped us from releasing it until October this year. So what I'm trying to say is people cleverer than me have thought about that, and I will go and ask them so that I don't have this problem again in future.
How does performance compare with some relational database? How this data is...
How big's your server? How much? It's kind of how big's your cluster. It's you're not comparing apples with apples, really. I mean, the easy answer is to say that this is a new technology that hasn't been fully tested in production. I mean, it's been tested by us, but it's not been put. So it's hard to answer something like that. I would expect, on similar data size, similar metal that you're putting it on, then you should kind of expect similar, but set up your indexes correctly.
Thank you,
But I think I've got to stop. Thank you.